Let's look at the computation of a tangent plane to a surface where the surface is actually represented parametrically. So now our parametric representation is u, comma v, comma u to the 1/2 times v to the 1/2. And we would like to construct a tangent plane at the point 1, 1, 1. Now when you compare the point 1, 1, 1 to our parametric representation, this would imply that u and v are actually both 1. And so the comparison between the point and the parametric representation is this. So this is important when we actually finish the calculation. And now for the surface normal, we actually take the cross product of the partial of r with respect to u with the partial of r with respect to v. So that gives us a very convenient computation to get a surface normal. And we will use that again when we talk about Stokes' theorem. Now the surface normal, of course, is just the cross product, and so we do the u partial of r, which will give us a 1, a 0, and then of course a 1/2 u to the negative 1/2 times v to the 1/2, which we have here. And then we have the b partial of r, which will be a 0, a 1, and then of course a 1/2 u to the 1/2 times v to the negative 1/2, which we have here. Now just to remind you, we've done cross products many times, so all of the theory that we used at the beginning of the course we're now using again. So there's nothing new to learn in this computation. So again, let's do the 2, 3, 3, 2. So we have 2, 3, that gives us a 0, and then the 3, 2 gives us the minus 1/2 u to the negative 1/2 v to the 1/2 as we have here. And then 3, 1 gives us the 0, and then 1, 3 we'll have minus 1/2 u to the 1/2 v to the negative 1/2, and then the 1, 2 gives us the 1, and the 2, 1 gives us the 0, so we just have the component 1. And now this gives us our surface normal. So the surface normal at 1, 1, 1 is actually the surface normal for r 1, 1, that is u is equal to 1, v is equal to 1. So here we do that. We replace u and v with 1. In the first coordinate, that gives us a negative 1/2. In the second coordinate, that gives us a negative 1/2. And of course, the third coordinate is fixed at 1. So again, we always need to make this computation so we know which actual values of the parameter to substitute to get the surface normal. And now we use the theory from the beginning of the course. We actually know that the surface normal will actually be orthogonal to this vector, because again, now we want to be able to realize in this particular case that the point 1, 1, 1 is an element of the plane. So we dot the surface normal with the vector x minus 1, y minus 1, z minus 1. Just like we did at the beginning of the course. And of course the orthogonality condition gives us the 0 here. Now to make the computation easier, these numbers are in the way, so just go ahead and factor a negative 1/2 from this vector, and that'll give you negative 1/2, and then we have a 1, and of course the negative 2, and then of course the negative 1/2 will just divide out, and we're done with it. So when we do the dot product, we have 1 times x minus 1, 1 times y minus 1, and negative 2 times a z minus 1, which we have here. And of course now we have an x plus a y, we have a negative 2 here, but then that'll be absorbed by the positive 2 here. And so we end up with x plus y minus 2z equals 0. So if you compare this computation to what we've done before, it's basically the same. The new part is that now we have a parametric representation of the surface. And we are done.